How many of you have been camping before? Pretty much all of you. Now, how many of you wish that you had a source of electricity while you were camping? Just a couple of you? Well, I personally know that while I've been camping, I wish that at night I could turn on a light switch to light up the campsite instead of walking around with a dim flashlight. So that's why for my senior project, I decided to create a portable hydropowered device. Before I began designing this device, I came up with what I ultimately wanted to accomplish, and that was to convert the kinetic energy of a river to power, to be able to store the converted power, and to distribute the converted power to correct electrical energy needed to ultimately charge a cell phone or run a string of lights. So once I came up with what I wanted to do, I wrote down the requirements. So because I wanted the device to be portable, I set the maximum weight to 35 pounds. And the device itself weighs a total of 21 pounds. So I was under that. And then I also wanted to make it so that it could be easily deployed into the river and not take up a bunch of time to get this power running. And so I set a time limit of 10 minutes. And when I tested the device, I was able to get it set up and running in under 5. I also set a maximum cost of $500, which I was way over. And I set a minimum requirement for the time that it should be able to create electricity of 2 hours. I set that time limit because the majority of the waterproof motors that I was looking at using had a maximum time limit of fully submerged of 6 hours. And then I also wanted to make sure that the device was durable so that it could be used on multiple occasions. So once the requirements were set, I began to design my device. And here is a three-dimensional Sulfurous model of the device that I came up with. So the device is mainly made out of a PVC tube which houses the turbine blade. Inside the tube is a turbine blade that is connected to a low-speed shaft. That shaft is then connected to a 130 volt 3 amp permanent magnet DC motor, which has a 14-to-1 gearbox. So after I came up with the general design, I then began to test in SolidWorks. And from SolidWorks, I was able to use Flow Express. And from this picture, you can see that the water flowing through is coming in contact with both the front and rear of the blade, limiting the RPM of the blade. So because of this Flow Express analysis, I determined that if I were to add a wedge in front, it would help stop that from happening and increase the velocity of the water flowing through the pipe, ultimately creating more power. Also, by using the Flow Express, I determined that if I made the shaft inside the turbine blade hollow, it also helped speed up the turbine blade because of the back pressure. So here's a side view of the device, and then here is a sectional view where you can see the wedge in front of the blade and the hollow center of the blade. So after the design was done, I began to construct the device. 3 key components of this device were constructed using a rapid prototyping machine. And here's an example. So this is the motor mount for the motor. And since the pipe is round, I was able to create that on this motor mount so that it would sit flush onto the pipe. And also I was able to download a SolidWorks model of the motor so that I could create a mount that would perfectly fit it. Here's a SolidWorks model of the turbine blade that I constructed. Here's a picture of half the completion of the blade. So a 3D printer works by laying down a layer by layer of plastic. And the base that the part sits on slowly moves down as the part is printed. And in here you can see a different colored plastic. That plastic is actually the support material that is printed so that the base material does not sag while it is printed and deform your part. That is then the support material is then dissolved in an acid bath to remove it, and you're left with your final part. Here's a short clip of 3D printing. So you can see it's just building one layer over the blade itself. The blade actually took, I believe, 30 hours to complete. Another key component that I constructed was the float. And I constructed the float by first making a mold, which I put U-bolts in, which could later be removed and used to bolt the float onto the device. In this picture here, I'm spraying mold release onto the mold. That is the mixing of the foam. Once the foam is mixed together, it's poured into the mold. So it took multiple batches of foam in order to fill up the mold because you can only do 4 inches at a time or else it'll become too hot and begin to combust. So once the mold was filled with foam, I then broke the block of foam free and was able to carve it into the shape of the float that I designed. Once the float was carved, I then covered it in a fine mesh fiberglass, and then that was then covered with epoxy resin to give it strength and durability. In order to test my device, I used 2 multimeters, one to measure the voltage and the other to measure the current, and a variable resistor. I also used a vernier flow rate sensor that would measure the velocity velocity of the river. To get a general on how this device would work, I used 3 different river conditions, and I found that if the river is not flowing faster than 2 meters per second, the blade itself will not spin. However, I've found that when it does flow faster than 2 meters per second, in the medium flow rate velocity, which I set at between 1.5 meters and 3 meters per second, I was able to create a maximum power of 190.35 or 68 watts. When the river velocity was sped up to faster than 3 meters per second, I found that I was able to create 120.59 watts of electricity. Here's a graph that shows the voltage versus current. And this shows that as the resistance is increased, the voltage is higher. And when the resistance is lowered and the current is increased, the voltage created is lower because of the drag on the motor. So it has a harder time spinning when a higher voltage is increased. When I connected the device to the 12-volt power source, which was a 12-volt 10 amp hour DC motor, I was able to create 18.25 watts of electricity because the motor limits the amount of voltage that can be used. And here's a short clip of the device in the water. I did have a flag connected to the shaft so that you could see the motor spinning, but once I stuck it into the water, it spun up too fast and broke off. So this is what I was left with. Any questions?